Were there any questions from last time about what we did? And it's time for me to also remember what we did. Base code. Okay. Any questions from the last class material? All right. Cool. Let's take a look at the base-catalyzed halogenation. And this one we're also going to see is going to sometimes be called the haloform reaction. And we'll see why that is. So we saw that if we, if we take I'm going to go ahead and just block off that position. We saw that we could, in acidic conditions, we could go ahead and protonate at that alpha position, right? We saw that we can go ahead and put a bromine on there. But we're going to see with the base-catalyzed one, the mechanism that it goes through actually makes it more reactive towards halogenation. So you will typically end up polyhalogenating your compound. And we'll see that sometimes that can lead to some interesting side reactions here. So we're going to see that if we do the same reaction in basic conditions, we can propose a mechanism for that. So we're going to do the same reaction with NaOH instead of H+. Okay, and so we're going to see here that it's going to follow pretty standard enolate type process. We will end up deprotonating, forming our enolate. Of course, equilibrium. All right, so we have our enolate species now, and it's going to come down and attack the bromine. Add a bromide. Apparently I'm using purple arrows today, so that's what we're going to do. And so now we end up with our brominated species here. And of course we lose a bromide ion, which will be picked up by the sodium. So the important thing here is last time the intermediate for this was not an enolate, right? If for the acid catalyzed one, it's an enol. So what we're deprotonating in the last mechanism, the acid catalyzed one, is the carbocation, right? We're eliminating with the carbocation there. And we have a strong, we didn't have a strong base present, so we needed a really good acid. We're going to see we have a strong base here, and we're going to see that these protons actually are more acidic now than the original 3 that we had, because that bromine there is withdrawing electron density. So because of inductive effects now, those 2 protons are even more acidic than the first one was, meaning that as a result, we're going to end up polybrominating this thing. Because there's no reason that the reaction would stop. It would actually get faster the more bromines you put on. So we're going to end up having all 3 on it. And now, interestingly enough, we now have a pretty good leaving group. I don't know if you remember, but CX3 was a strong deactivator in our benzene. If you remember your Hoffman elimination, we have some unusual leaving groups. Suffice it to say, the Hoffman elimination, remember, we had NR3 as a leaving group. In this case, we're going to have CX3 as a leaving group. And so we see that because it was a strong deactivator, we know that it pulls a lot of electron density. So it's actually going to be relatively stable as a carbanion. So what's going to happen is an OH is going to come along, which we have plenty of, because this is under the basic conditions, right? Comes and attacks this, opens it up, and we're going to go ahead and form our tetrahedral intermediate. OH, and then we have the carbon with all the bromines. And actually that's, like I said, it's going to be our leaving group here. So we're going to actually close down and we're going to kick out that carbon with the 3 bromines. This works especially well with iodine. You see this iodoform was a pretty common chemical test back before the days of IR. And then, of course, this thing is just going to deprotonate our acid. And so we end up with the carboxylate, and in this case, this is bromoform. Like you've obviously heard of chloroform, right? CHCl3. Bromoform is the bromine equivalent. I'm sorry, Bailey. And then iodine, or the iodide one would be iodoform. And while bromoform and chloroform are clear, colorless things, iodoform is this bright, powdery yellow thing. And so it was a very easy way to tell if you had a methyl ketone in a molecule, because you would see that it would react and it would form this bright yellow powdery thing with iodine and in base. So we see here that, of course, if you wanted an acid wash, by the way, actually a water wash would probably be okay, but we'll do an acid wash just to be safe. You'll end up getting your carboxylic acid out. So it's a way to, we end up starting with a methyl ketone. So one side of our ketone had a methyl group, and we're going to end up with a carboxylic acid. So that's the kind of transformation that takes place here. A methyl ketone becomes a carboxylic acid. If you don't have a methyl ketone, and you were to do this, you would probably just end up with the dibrominated species. If you had something like this, you'd probably end up polybrominating this thing all over. So you'd end up just brominating everything. And that's not good enough to be a leaving group, just having 2 bromines on there, so you don't end up forming any carboxylic acid like you do with the methyl ketones. So non-methyl ketones or aldehydes will end up as just polybrominated species. So the point is here, if you want a carboxylic acid and you have a methyl ketone, here's a way to do it. If you only want 1 bromine on, don't do this reaction. Use a different one. You can use the acid catalyzed one. That'll just put 1 bromine on, or a stoichiometric equivalent thereof. So with this one, you're going to get a mess of products depending on how much bromine you have in there. So best to just do it to excess if you want this polybrominated thing. Like if you're going to make like alkynes or something out of this, then maybe you want it polybrominated. So that's the idea here. All right, so it's something that just keeps on going. All right, so again, for methyl ketones, you'll end up with a carboxylic acid. For non-methyl ketones, you'll get polybromination happening here. Okay, so that's things to be aware of. Right here, let's make it big for a second. Okay, let's go through the mechanism just one more time to be sure. So, first step, base-catalyzed, is to remove a proton. You form your enolate, excuse me, which then acts as a nucleophile, attacks bromine. Do this several more times, and you end up with 3 bromines on that, which now we're going to use as a leaving group. So your base will come in and attack your carbonyl. It's going to close down and kick out the CBr3, leaving you with the CBr3 anion, which will then deprotonate your acid to form the halo form. In this case, it's bromoform. And you'll end up with the carboxylate, which then you'll treat with acid to give yourself the carboxylic acid. Okay, so that's the mechanism for that one. So now we can turn ketones into carboxylic acids. Exciting. Other ways to do that, by the way, how else could we do this? Oops, that's not a ketone. That's it. That's no. Here, we'll make it really easy. How else might we turn this thing into a carboxylic acid? I'll give you a hint. No, I won't. I won't give you a hint. How might we turn this thing into a carboxylic acid? And no, you cannot just throw any old oxidizing agent on this. It's a ketone, right? So how else might we do this? So you see now we can do it with Br2 and AOH, acid wash. That'll do it. How else? This would be stuff that we've learned previously. One reaction from exam 2, one reaction from exam 3.
Would we be able to use
Not on the ketone directly. So thionyl chloride on ketones doesn't really do much. So what do you think? How else might we get this to happen? One of these was a question on your last exam that a lot of you misinterpreted, kind of. NAS. Nucleophilic aromatic substitution? What aromatics do you see here? Yeah. Yes. So, okay. It was not that one. Maybe if I give you the first reagent, what does this do? What does that do to a ketone? Turns it into an ester, right? How do we turn an ester into a carboxylic acid? Oh, come on, this is not that hard. Well, the opposite of that, yes. So esterification makes the ester. Just putting water will hydrolyze it. So hydrolysis would be the other one. So that would be another way to get this. So now we have two ways if we wanted to make a methyl ketone into a carboxylic acid. Although the Baeyer-Villiger followed by the hydrolysis would work on bigger non-methyl ketones. So this bromoform or iodoform, whatever haloform reaction, only works on methyl ketones. So this one can work on non-methyl. This is methyl ketones only. And iodine would be the more reactive one. So bromine works, iodine works. You can probably get away with the chlorine too, but iodine would be your best bet. Okay, so cool. So a little bit of review. So don't forget these reactions, right? Speaking of forgetting them, here's a few more because we need more reactions. All right, here we go. This is the Volhard Zielinski bromination. Carboxylic acids. We're not going to worry about the mechanism for this, just the reagents. This is here because this is an alpha proton type reaction. So we're going to treat our substance I say, Br2 and PBr3, followed by water, and we will end up brominating our alpha position. How this does work, by the way, is your PBr3 will turn this into a acid bromide, which then will tautomerize into the enol, which can then attack the bromine and then go from there. And then the last step is to hydrolyze it back to the acid. So this works out nicely, and you'll end up getting a bromine specifically on your alpha position here. Works out nicely. So this is for acids specifically. This is not going to work on ketones, aldehydes, whatever. This is for carboxylic acids. So keep that in mind. All right. So there's another way of putting a halogen on to an alpha position. Okay, so we've learned 3 ways now. We can do it with acid on a ketone or aldehyde, or maybe even an ester. We can do it with base on one of those 3 things, or we could do the HVZ reaction on a carboxylic acid to, again, get that alpha proton to be brominated. So, questions on any of the bromination or halogenation, I guess I should say? Alrighty. We shall go on to probably one of the more useful reactions, which are aldol reactions. Of course, the name is not after a scientist, as so many are. This is after aldehyde alcohol. That's where the name comes from. So aldol. And these are going to be your products. Although we will see we can get ketones in alcohols as well. And this is essentially a reaction that an aldehyde will undergo with itself in basic conditions. So we're going to see that if we treat an aldehyde in basic conditions, we're going to see something interesting happen. So 1, 2, 3, 1, 2, 4. We're going to see that we get something interesting happening. So we're going to have an enolate form on an aldehyde, and it's going to attack another aldehyde, basically the same molecule that it used to be. And it's going to end up yielding an alcohol on one of them and an aldehyde on the other. And we're going to see here that the new bond that's being formed is right here. I've drawn it so that it's relatively easy to see. But these are very, very easy for me to rotate things and confuse you. So how you can identify an aldol has happened is this, oops, should I put a dot there? We have 2 carbons in between our aldehyde and alcohol. That's kind of your clue. If you want to include the main carbon on the aldehyde, it's a 1,3 type of process. Aldehyde 1, alcohol on the 3rd carbon. So this is a 1,3. Am I going to call this an addition? Yeah, I guess I can say that. So we're going to add it to the beta carbon. The beta carbon will have the alcohol off of our aldehyde. So let's take a look at the mechanism. Go ahead. Yeah. Between your aldehyde and alcohol. So aldehyde, alcohol. 2 dots in between. And then if you want to count the carbon as part of the aldehyde, it's technically a 1,3 addition, but there's 2 carbons in between the functional groups, if that works. So first step for the mechanism. As this chapter is on enolates, we are going to form an enolate. That enolate will see an aldehyde. This is a good nucleophile. This is a good electrophile. So there's no reason they wouldn't. I'm using blue ones apparently this time, so here we go. I'm going to go ahead and attack our carbonyl carbon. Pop that up. I have no room, but let's go ahead and see here. So our aldehyde stays, our original aldehyde is, or one of them will stay exactly as it was. And now you see here, we're going to end up forming a bond between the purple carbon here and the purple carbon here. And so we're going to see here that that's going to be this carbon, and we need 1 more carbon, which is going to now carry our alcohol. So there's our new carbon-carbon bond. We have the alcohol there, because that's what used to be the aldehyde. Actually, I guess it's an O- right now. And then we have the rest of the molecules. So we had 3 more carbons on the other side, so 1, 2, 3. And then we have, I'm going to draw the other one as purple so we can see that's our new bond that's formed. And then we just need to protonate it. We have water nearby, so be a good choice. So we regenerate our base catalyst, and we end up, I think this is technically still equilibrium, we end up with our product. So notice we had 4 carbons before, we now have 8 carbons in our aldol product, and we have an aldehyde and an alcohol. Let me go ahead and make this super big. So an enolate type reaction. We have our base deprotonate our aldehyde. forming the enolate. The enolate is a pretty strong nucleophile. Our aldehyde is a pretty strong electrophile, so those will react right away. They will form a new carbon-carbon bond between the alpha carbon of one of the aldehydes and the carbonyl carbon of the second aldehyde, giving us our product there. And then we will have the protonation step at the end. So the new bond, again, that's being formed here is between the alpha carbon of the aldehyde and the carbon that has now got our alcohol. And so we'll look at a couple of examples of what to do. But I do want to say that this isn't... Go ahead. Sure, I can do all sorts of fun stuff. Let's see. No, I could do all sorts of like weird. Here, I'll even do it this way. Like weird stuff, right? The point is that you'll look for an aldehyde and an alcohol and see how many carbons apart they are. And so if you have a beta alcohol on an aldehyde, that's a pretty strong indicator that you've got something happening here in the form of an aldol type reaction. I could also draw it like this. Oh, I totally have forgotten the carbon. That's too many carbons. So, tons of different ways I could draw this thing. And that's the ugliest oxygen I've ever drawn. There we go. So, what you're looking for is a beta alcohol. That's a pretty strong indicator you've had an aldol happen. Especially since these have the same number of carbons on each. We'll talk about mixed aldols later, but for just self-aldol reactions, they will have the same number of carbons. Cool. So those are some examples of how I might be able to rotate this thing so it's less obvious, maybe. So, yeah, fun stuff can always happen. All right, so, and then if I feel like it, I could also give you stereochemistry. Ta-da, there we go. Just to scare you, as always. Since this comes from an enolate, the sp2 carbon attacking an sp2 carbon, of course, it's racemic. Although we will see that this is usually a syn addition, but that's beyond the scope of the course, so we're not going to really worry about that. So, go ahead. Yeah, alpha, beta. So alpha carbon is one carbon away from your carbonyl. So this is our beta hydroxy, and here is our aldehyde. Right? Or, I mean, either way, alpha, beta. Yeah, so just 2 carbons away from your carbonyl. Okay, so this is an equilibrium process, I will mention as well. For aldehydes, typically the product is favored. But for ketones, it's generally the reactant that's favored. So I'll just make a note of that, and we'll look at a ketone example in a second here. For aldehydes, the product is favored. Really? So for aldehydes, we're looking at the product, generally speaking, is our major species present in the solution. However, in the case of ketones, generally speaking, we're looking at the ketone still being the predominant species rather than the aldol product. So we'll do the same thing. We'll even use our fun thing here. If we're going to try and think what's the aldol product here, we're going to keep one of our things the same. And then we're going to now put the other, another copy of this molecule on with an alcohol instead of a ketone. So this is our original molecule. I'm going to draw our ketone carbon, which is now an alcohol. And that ketone carbon had a methyl group, and then it had that T-butyl group. So our new bond that we formed is right here. It's between the alpha carbon and the carbon containing the alcohol. And so we're going to see here, in this case, that the equilibrium, which I've neglected to draw, will actually favors the reactants more. So this reaction is less likely to happen. So we don't see ketol products as much as aldol products, simply because the ketones are less electrophilic. They're kind of happy to stay as they are. They're also less acidic. So they're worse nucleophiles and they're worse electrophiles. So it's just less. It's going to happen less frequently. And now just to throw a wrench in everything, let me just write that, by the way, ketones. Okay, so we will typically favor the ketone over the aldol product of the ketone reacting with itself. Correct. So ketones will generally stay as ketones in the presence of base, whereas aldehydes will typically form your product, your beta hydroxyaldehyde, in the presence of base. So this reaction generally is not going to really go forward. You're typically not going to see this happen. So, yeah. That being said, we can take advantage of this by doing what's called, since it won't do an aldol, it would then be a candidate for a retroaldol, do the opposite of the aldol and break it apart into ketones. We can do a retroaldol in the presence of our base, and that would split this apart. So if you have an aldol product that came from a ketone, i.e. you have a ketone, it's a beta hydroxy ketone, not a beta hydroxyaldehyde, you can actually split that bond, forming your ketone. You'll end up with two of these cyclohexanones. So because the equilibrium favors the reactants, if you already have the product, you can convince it to go into the ketone form. So we have a beta hydroxy ketone here. So again, 2 carbons away. And this would just be a plain old ketone. We have 2 separate ketones there. So you can take advantage of this fact by doing a retroaldol, by taking a beta hydroxy ketone, treating it with base, and you'll end up with just your ketone. And if this were asymmetrical, say instead we had if we had something like this, and we treated it with NaOH, we would end up with 2 different ketones. We would end up with that cyclohexanone. This is the bond that's formed, so we just have the rest of it. We have, what is 1, 2, 3, 4, 5 carbons. Wait a second. Oh, did I? This should be on the. I'm sorry. I've drawn too few carbons. We actually have our cyclohexane here. Yeah. Sorry. Let me make that a better cyclohexane as well. Because obviously that other one would just come from an aldehyde, right? So we need another carbon here. There we go. So because you're going to end up with a tertiary carbon, since your ketone already has two carbons on it, you're adding an additional carbon-carbon bond. So it has to be a tertiary alcohol. So my bad. So sorry for drawing that wrong. So with this, we end up getting our two products out. We'll have two separate ketones because this particular beta hydroxy ketone was not symmetrical, meaning it didn't come from the same molecule as we see in the upper case here. Water's involved as well because you need something to protonate at the end. These are typically done in aqueous solution. Have you done this in lab yet? The aldol reaction, aldol condensation of what is it? Gosh, I can picture it in my head. The benzene, the dibenzyl acetone. No, not yet. You did it yesterday. Well, there we go. So yes, but if you remember, I don't know if you did a video, but you use like, I don't know, like 10% sodium hydroxide or something in water. So yeah, you definitely have water as like a solvent there, for sure. Now that's an especially useful one because benzaldehyde can only be your electrophile, so it's quite useful that way. But we'll talk about that. Okay, let's do some practice. Let's how about we do let's do an aldol on this one, even though it will prefer the products. What's the product going to be of this thing? And yes, I will write the water. That's the best part about paper OChem is I can do whatever I want, right? So, predicting aldol product. First thing, just copy your original molecule. At least, or not at least, one copy of your original molecule will be there, present in the product. And now you draw your new bond will be between your alpha carbon. In this case, we only have one option because only this one has hydrogens, right? So if you remember the mechanism, it goes through an enolate, so we need to go from the side that has the hydrogens. So we're going to make a new carbon-carbon bond here to the same molecule. And so we can draw the same molecule. And we know that that carbon-carbon bond is going to be formed between the alpha carbon and the carbonyl carbon. So that's where our alcohol will be. And then we just have to stick on the rest of the stuff on our molecule. And those methyl groups could be on the bottom carbon instead. Doesn't matter if it's rotate, but it's not a problem there. So the blue bond there is our new bond that we're forming here between these two molecules. Yes, I get it. There's a software update. Thank you for reminding me every 2 seconds. So are we seeing this? Relatively straightforward. Any questions on these? Mm-hmm. Yes, it's always one carbon. It's the one that will be the new beta carbon. Yes. So it will be between the alpha carbon of one molecule and the carbonyl carbon, which will become the new beta carbon. I could have put them over here. I could have put them down here. No problem. We just know that they're one carbon away from the carbonyl, right? So if I have like a fluorine down here or something, like I just need to have the fluorines next to the methyl groups. All that stuff just stays the same. So the only thing that's changing is we're forming a bond between the alpha carbon and the new one. So one way you might do it is you might just draw two copies of it. I'm going to just rotate this one, actually. Can I do that easily? No. Oh well. The new... Ugh, that's terrible. Maybe I can rotate it if I do it like this. There will be no rotation. Then it sucks that I've got these methyl groups in the way. But I'm going to just draw them on the other side. I know I just said just copy the molecule, but like I want it to be as clear as possible. So the new bond that's going to be formed is always between your alpha carbon and your carbonyl carbon. So you're just drawing a bond here. This one then becomes the OH, and everything else stays the same. That's the only thing that's happening there. So we're getting rid of an H, one of the blue H's, forming that new bond, and that second carbonyl becomes the OH. And everything else in the molecule stays exactly the same. Yeah. I mean, if you don't have all these substituents, you don't even need to flip it. Like if we're just doing cyclobutanone, or take two of them, form a bond between here and here, and turn this one into an OH, and you're done. I mean, of course, that's a terrible bond, right? But you would just redraw it. You'd say, okay, well, I know I've got this. So I rotated the second one slightly just to make it so it makes more sense, but that's the new thing. So just redraw it with that purple bond there, and you're done. That's all you need to do. Mm-hmm. Alrighty, good news. We have another step that is potentially going to happen. We're going to see that condensation will take place. And if we take a look at, I mean, we can even look at this particular one that we just did. If we do the same thing, and heat it up, we're going to see that, yes, our kind of first step is, these are the most terrible squares I've ever seen. There we go. First step is making the aldol. But what will happen now is in the presence of heat, we're going to actually condense this thing and eliminate. We're going to have an elimination process take place here, which will end up giving us a double bond instead of that hydroxy. We'll end up with we'll end up with a double bond there instead. So we're going to end up eliminating and kicking out our hydroxy group, forming now a double bond. And I'm going to really redraw this because the geometry is just killing me. That's not very good either. Okay. We're going to do this really, really nicely. Boom, look at those squares. Yes. Ta-da! So, there we have it. That would be our product after the heat step is involved. So if you have heat here, you're going to end up making your beta-hydroxy ketone or beta-hydroxy aldehyde. And if you have heat, you are going to condense. Condensation happens in one more step. Have your alpha proton. You end up eliminating. You already have hydroxide present in this, so it's okay to have hydroxide as a leaving group here because you're just regenerating your catalyst, as it were. And so you'll end up favoring the elimination product, and you'll end up with the double bond instead of the alcohol. So now we have an alpha-beta unsaturated ketone. And of course, this will work with aldehyde products as well. And it's really just the addition of heat that's the only difference here. And so instead of the hydroxy group on the beta position, you'll end up making a double bond between your alpha carbon and your beta carbon. And we'll look at a couple more examples. So the only thing that's done is we've added heat. Heat will now favor elimination. Elimination is the removal of a substituent to form the double bond. And so this is the thing. You actually did an aldol condensation in your lab with the dibenzyl acetone. So it is indeed an aldol condensation that you did. And in fact, we can, I'm sure you guys spent way too long on the mechanism for that anyway, right? Or do we want to do that as an example? Y'all let me know, otherwise I will just do this one again. So if we're to do this in the presence of heat, we saw our aldol product. This is one we've done before. Nope, this is the condensation. So all we're doing, it's an aldol condensation. So instead of making the beta-hydroxy ketone or beta-hydroxy aldehyde, we're still using the same aldehydes, like two molecules of it. So like that cyclobutanone attacked another cyclobutanone. These are not mixed yet. Mixed ones would mean we're having something like this plus another aldehyde or something. That would be a mixed one. So if we just have our single reactant, it's not mixed quite yet. So first step, make your aldol product. Second step, replace your OH with a double bond on the between the alpha and beta carbons. So keep that part the same. And I guess we should probably prefer the trans product here. That's just stereochemistry, right? Stereochemically preferred to make the trans product. But we're going to end up eliminating. So we, in the presence of heat, you will eliminate your hydroxy group, giving you the double bond. And as always, the trans product is favored over the cis product. So you will see that your major product will always be your trans product. do another one. Use acetophenone. If we make the aldol product, draw our molecule exactly as it was. And now we're going to draw a new bond between our alpha carbon. Let me move this over just a little bit. Between our alpha carbon and the carbonyl carbon. So that carbonyl carbon on it will have the OH. Let's look at what else our carbonyl carbon had. It had a methyl group and a phenyl group. So we have a methyl group and a phenyl group. And so we will end up, this is a carbon in between. I hope that's obvious. Oh, it's ugly. There we go. So we're going to end up with, this is our original aldol product. And if we want to do the condensation product, we will just get rid of our hydroxy group. And now we've got a double bond there. That methyl group is still there, and that's, the geometry is all terrible. And we're going to draw the trans double bond. So our phenyl group will be trans to the other acetophenone component of this. Worst case, just do the mechanism. Mechanism will get you the right beta hydroxy ketone, and then you can just remove the OH and replace it with a double bond with the alpha carbon. These are much more preferred reactions than the regular aldols are. So you will see these happen more so than, like with ketones. Remember, we don't really see those doing aldol very much. But if you apply heat, they will do the condensation reaction. And they will do that pretty nicely. So you will favor the product there. All right. So questions on those? Before we look at some more. All right. Then let's now look at mixed aldols, where you're going to have two different aldehydes or two different ketones in there. And so we're going to see that we typically will use aldehydes that don't have alpha hydrogens, sorry. So typically for these, we want at least one, well, we need one rather. With no alpha protons. And the reason for this is because if you did have if you had one aldehyde with alpha protons and a second one with alpha protons, there's really no reason to choose one over the other. You're going to get a mix of all sorts of crazy products. You're going to have something reacting with itself. It'll react with one as the nucleophile. It will react with another as the electrophile. And the other ones can react. You're going to end up with like 4 different products, all of which are racemic. So you typically will want one with no alpha protons. So that would be something like formaldehyde or benzaldehyde. Neither of these have alpha protons. So these are good candidates for mixed aldol reactions. Because, whenever we form a mixture of products, it's kind of useless. It's a pain to separate them, and we will have lost like the majority of our product to side reactions anyway. So typically we will go ahead and go through this. So if we want to use formaldehyde, we can do that. We can say, let's take Let's take butanone here and formaldehyde. And if we put them in NaOH, we'll look what happens. But let's analyze these compounds. If we were to compare which one of these is the better electrophile, we would remember that aldehydes are better electrophiles than ketones are, right? Because they are less stabilized. There's no hyperconjugation stabilizing the resonance form that has the carbocation. So they're more reactive, right? So this is the better electrophile. And because it has no alpha protons, it can't be a nucleophile. There's no alpha protons to remove, so you can't make an enolate of this formaldehyde. And so it's going to be an electrophile. And so because it's the better electrophile than the ketone is, because ketones are also electrophilic, right? They have a carbonyl-carbon, you can attack it. But if you have the aldol or enolate form of this, which I will draw right now, okay, and I just drew exactly the same thing. Let's try that again. All right, if you have the enolate form, that enolate can either attack a ketone, the butanone, or it can attack the formaldehyde. And of course, because the formaldehyde is more reactive, it's going to prefer to attack the formaldehyde instead. And so, although this was kind of a interesting choice, we'll end up attacking. We're going to end up making it so that we have our ketone originally stays. Our alpha carbon is now connected to the carbonyl carbon, which just had the two H's, and the carbonyl, which becomes the new OH. So when you're doing a mixed aldol, you have to choose what's your better electrophile, because that's what your nucleophile is going to go after. So that's why you want an aldehyde in here, specifically an aldehyde that can't act as a nucleophile, which means you have a lot of it floating around, ready to be attacked. And so it's simply a matter of kind of convincing this to happen. All right, so you can go ahead and do that. And if we were to condense this, we could, but we would need the heat for that. If we were to condense this, condensation product would just be this bizarre double bonded one. This would be the condensation product if we put heat. So we didn't put heat this time, but I'm just showing you if we did, we would end up with this instead. All right, so do we see why that happened? Of course, we could have it happen on the other side as well. We could have one of the other alpha protons work. We could have had it be this way instead. But we're going to see here that the other one is preferred. Right, we could have this attack our formaldehyde instead. Comes down, attacks, opens up. And in this case, we're going to now have our bond over there. So, and if we were to make the condensation product there, we could do that. But this one is going to be this is going to be a minor product. Why? This will be our major product here. Why is that our major product? And why is the other one our minor product? What do we think? Any idea? Yes, you're correct. What were you going to say, Eric? Very good, yes, because our double bond there is more stable in the enolate, so this is the more stable enolate, more likely to form. And so we're going to end up with that one being our preferred major product. So this is our more stable enolate than the other one, so we're going to end up doing that. All right, so let's say you did want to do a mixed aldol with something that did have alpha hydrogens. So that's option one. You can either have an aldehyde that has no alpha proton, so either formaldehyde or benzaldehyde. But if you want your mixed aldol to be with one of these that's not one of those two molecules, let's say you have the cyclohexanone and propanal. If you want that, how might we get this to work? Well, unfortunately, if we just throw this in with base, we're going to get a ton of products out of various different ones acting as nucleophiles and electrophiles, and it'll be a pain in the butt. So what you can do is get rid of that. Depending on which way you want it to go, which one you want to be as the nucleophile, say we want our cyclohexanone to be the nucleophile, what you would do is you would treat this with either KH or LDA. And we'll see later on why we'll choose one over another. But we'll see that later. Remember that this is an irreversible deprotonation. This is irreversible. And so, if you put in the stoichiometric equivalent of KH or LDA, it will react with all of your ketones, making them all into enolates. And as a result, there are no ketones left. This cannot react with itself because there are no ketones. They've all been reacted with your base. And so this thing is just kind of chilling here. It's waiting. And so now what you can do is put in your aldehyde of interest or ketone. I used an aldehyde in this case. And now we're directing it so that our nucleophile is must be the cyclohexanone, and our electrophile must be the one that we're adding in after. So what's going to happen is, pops open. I'm going to have to draw this one down, I guess. So our O is back here. We now have 1, 2, 3 carbons that we're putting on. The first one will have the OH. So that's 1, 2, 3 carbons overall. And that will be our product here. Of course, we can condense it if we put the heat as well. So just remember, aldol and aldol condensation, the only difference is the presence of heat. So if you have heat, you're going to draw the condensation product. Without heat, draw the aldol product. I will write that. Oh, that's some terrible little arrows. There we go. I'll just write this beta hydroxy. So if you do have the heat, you will end up making the double bond. That's the condensation. Without heat, you'll make the beta hydroxy species. So this one we do not have heat, so we would then make our our beta hydroxy species. So this is what's called a directed mixed aldol. We're directing which one we want to be the nucleophile, which one we want to be the electrophile. We can do this the other way. We can say, I want that aldehyde to be our nucleophile instead. We could do that. We would just change the order of steps. We would put our aldehyde in first. We would put our KH in, or LDA, either one. You make your enolate, and now you add in your electrophile. In this case, it's the cyclohexanone. Comes down, attacks the carbonyl, pops it open. So this is going to be a bit messy, but here we go. We now have our OH and then cyclohexane there. And so we would end up with this as our product. So you see here that we end up with two different products, right? We had one of the cyclohexanone and then we added on this alcohol component. In this case, we will end up with our alcohol on the cyclohexane. And we'll have our, whatever that is, propyl thing, will be our kind of a main chain. So you see how we get two different products this way? By directing one to be the nucleophile, by using a strong, irreversible base. Remember with NaOH, we talked about this as it's going to cause an equilibrium, right? But some of these stronger bases, KH or LDA, will force you to fully deprotonate your aldehyde or ketone, and you'll end up now with an enolate that can't react with itself because it's fully reacted already, and then it's just waiting for an electrophile to come around. Alrighty. Shall we do some practice? I think so. All right, you're going to tell me what our starting material and reagents will be for a couple of problems. So let's say I have how would I have made this thing? So I'll give you a moment to work on it. First thing I would advise you to do, by the way, is to figure out where your bond is made between the two molecules. Where are you cleaving this in your retrosynthetic analysis of it? Starting material. That would be potentially one. So this is a mixed one, right? So that could be our starting material. So you have to make the choice. Which half of the molecule will be your starting material and which will be the other one? And so up to you. All right, so hopefully by now you see that this is the new bond that's been formed, right? It's between our alpha carbon of one species and beta hydroxy. So hopefully at least you got that part done. I'm going to go ahead and agree with Audrey. I think that our cyclohexanone will be our ideal starting material. We know that because the part that has the double bond must be the nucleophile. The nucleophile retains its double bond O. The electrophile is the part that will have the hydroxy group. So this part here is our electrophile. And so if we're to redraw that electrophile, let me not draw this one in blue. So our nucleophile must have been this dude. Our electrophile be everything. We have a methyl group, we have another carbon, and then that was an aldehyde, right? We knew it's an aldehyde because we have another H there. If we had a tertiary alcohol, that must have come from a ketone. But because this is a secondary alcohol, the secondary alcohol means that we started with an aldehyde as our electrophile. Does that make sense? And then from here, what reagents do we want to use to get these two to come together? Yeah, NaOH will work for this one because our electrophile does not have any alpha protons, so we are good to go ahead, and our electrophile is already a better electrophile than our nucleophile is, so we're going to say that NaOH will work here. And no heat, of course, because otherwise we would end up with the other one. All right, questions on, yeah, go ahead. Not a good idea here, not necessary. So remember, you use KH or LDA if you don't have this scenario here. If we don't have an aldehyde with no alpha protons, then we are going to have to deal with KH or LDA. But because our aldehyde here does not have alpha protons, no protons on that alpha carbon, we are okay to use NaOH. And remember, if we can use NaOH, we should. Because it's much safer, right? So it would be a waste to use KH on this. And you're putting things at risk for no reason. So, and I guess the question through all your minds is, yes, there would be points off if you used KH or LDA here. You want to use NaOH because you can. All right, if we did have something like this, then NaOH would not be a good idea. Then we would have to use KH or LDA, and we would have to do it stepwise. But because this one has that methyl group there, there's no alpha hydrogen, we should use NaOH. All right? Let's do another one. This time let's predict the products. I'll give you a moment to work on this. And in this case, I'm going to add one more word here. I'm going to indicate that this reagent, our starting material, is dilute. Dilute is a key word that's going to tell us this is an intramolecular reaction. So dilute is our keyword for intramolecular. So I want you to do this reaction intramolecularly. There are going to be two products here, but we'll see that one will be better than the other. Right, so just in the interest of time, we'll go ahead and finish this. So we have two potential enolates that can form, right? We could form one here. And I'm going to just draw one on one side because it's symmetrical, right? So it would be the same if we did it on the other side. But these would be the two that we would form, right? We could form these two enolates. And so if we were to go ahead and react this with itself, the product we would make for each of these, we're going to see we're forming a bond between these two. So we are going to end up with this terrible, terrible molecule. And since it's with heat, we would end up with the elimination product. Right? I'm going to technically draw this one just down just for for the fact that it's trans. That's kind of terrible, right? However, if we look at this one, we're going to make a 5-member ring. Carbon 2, well here, let's go ahead and number these. Carbon 2 is the one that will have our double bond O. Carbon 1 and 5 are now connected. 5 will now have the hydroxy, but since this is with heat, we are going to end up eliminating, so we're going to end up with that. And then we had another methyl group on carbon 5. So while technically the one on the left is the more stable intermediate, do you really think we're going to form this product on the left? Probably not. Cyclopropanes are not really ever a good idea, especially now that we have a double bond in there, so it's just going to make this thing a whole mess. terribly strained molecule. So even though that this is the more stable enolate, this one is completely unstable. 3-member rings are never a good idea in OChem, right? They're always going to be reactive. They're going to just break apart as soon as, a gust of wind comes along. So not really a good idea. So in this case, we're looking at the product stability. So remember, the more stable intermediate will give us our kinetic product, and that may or may not be the same as our thermodynamic product. And as we can see here, this cyclopropane thing is really just not a good idea. It's probably not going to form very, very readily. So our major product in this case is probably going to be this one, especially since we're, heating it. Since we're heating this thing, that ups the chance that we're going to get a thermodynamic product, right? So we tend to look less at kinetic products when heat is involved. So even though we have the less stable enolate, we end up with a much, much, much stabler product. And so that would be our major product. Okay? Questions on that one? Mm-hmm. Mm-hmm. Yeah, so so if we take a look, this might be the we might draw these. Oh, that's terrible. Okay, let me try this again. Okay, so you're having two competing reactions happen, right? And let me try to draw that again a little bit nicely. This one here is our kinetic product. So if we think about energy as an axis, if we're drawing it as a graph, and this is our reaction progress as our reaction is taking place, this purple one is our thermodynamic product. So our kinetic one has a lower activation energy barrier to overcome versus our thermodynamic one. And I'm just, these are just generic, there's no numbers involved here, but that means the kinetic one, the intermediate is formed faster because more molecules will have sufficient energy to overcome that activation energy. And so it can go ahead and react. But remember that this is an equilibrium process. It's an equilibrium process, which means that it's going back and forth. And remember that because it's got a lower activation energy hump, it can go backwards easily. Go backwards more easily than the thermodynamic one can. Because if you then look at the activation energy for the reverse reaction, that would be here, right? Again, these aren't real numbers or anything, but the activation energy for the thermodynamic product to go all the way back would be the biggest of all. So it's super unlikely to happen. So it's all a matter of statistics. Some amount of molecules have enough energy to go the kinetic route. Some molecules have enough energy to go backwards on the kinetic route. Fewer molecules have enough energy to go on the thermodynamic route, and probably none of the molecules have enough energy to go backwards on the thermodynamic route. So it's simply a matter of this thing forms and then it immediately breaks down back into this thing breaks back down into this thing, and then it has a choice. It's either going to react the same way or it's going to react to make the thermodynamic product. So it's just a balancing game and statistics, if that helps explain that a little bit more. Yeah, it just goes right backwards. Yeah, it just goes right backwards. Cool. Okay. Awesome. Then we will, I guess, see you guys Friday. We'll do 9 o'clock review session. Bring questions. on your amines and carboxylic acids. Don't forget those SIs are on Discord here, so go ahead and go through them. That's good practice, and bring questions on Friday. All right, we'll go for about an hour on Friday. So, alrighty, take care. Enjoy the rest of your day. Yeah, just Mondays, not on Wednesdays. I go to USC on Wednesdays, so I don't have time, unfortunately. All right, see you later.